This video will continue our discussion of section 2.4 with a couple more examples. One example will be just a DE, DiffEQ, finding a general solution, and then we'll do an IVP. All right, so it says solve the following DiffEQ. First things first, when I see this and I have the 0 over here, my first thought is it exact? If it's exact, then it's going to be easier process. So I'm going to write down my m, xy, and that equals 2xy squared plus 2y. And then I also have n of xy. And n is going to be 2x squared y plus 2x. So I take my partials. Remember, it's the other one. M is with dx. I do y. So my would be, okay, so we got 2 comes down. I get a 4xy plus 2. And then if I do n of x, I get 4xy plus 2. So that means, therefore, that's what the 3 dots mean. DE is exact. Then there exists some function. There exists a function f such that partial of f, here we can write shorthand, fx, that's partial of x, is m, and fy, partial with y, is n. So then I can find f of xy by just taking the integral of m dx. All right, so 2x y squared plus 2y dx is going to get me okay, I go up by 1, divide by the new one, so that's x squared y squared plus 2xy plus h of y, not c, right? Because this is my m that I took the derivative with respect to x, so there could have been a y out there. Okay, then I'm going to actually go ahead and find that partial of my new function I came up with respect to y, so I get 2x squared y plus 2x plus h prime of y, and then we set this equal to n. All right, I'm going to do that here. N is 2x squared y plus 2x. And you can see this should happen if it's exact. All that should go away, and I might have something on the right for y, but in this case I don't. So h prime of y is equal to 0, which means h of y, if I take the integral, do not say 0, it's c. All right, so then our answer is just going to be whatever f was, right? That's x squared, y squared, I'm getting it from here, x squared y squared plus 2xy, and then I know that it's going to be a c, so I'm just going to put that over there. And there is my solution to that diffie. So remember, it's self-checking. You could take the derivative with respect to x, it should be the m. Take the derivative with respect to n, it should be your n. I think I said with respect to n, and I meant with respect to y. I'm not sure. Okay, so 2.4, we got one more here. This is going to be an IVP, and then we're going to work on a method that if something happens, we can actually use exact. Okay, so this IVP for, let's start mxy is 2x minus y. So that tells me that my is -1. N of xy, which is 2y minus x, that's going to also, n with respect to x, is going to be a -1. So the DE, therefore, is exact. All right. So I like writing these statements out that I did in the last problem that I have been, because it just helps me know where to go. So then there exists, a big capital E backwards E, there exists a function f such that f of x equals m and f of y equals n. All right, so I have that. So I can find that function then by going backwards. I can take the integral of m with respect to dx. All right, so that's going to be the integral of 2x minus y dx, which is equal to, okay, that's going to be x squared minus xy plus h of y. Remember, I don't know what it is. It could be some term of y, ln of y. It could be y squared. We don't know. Right, so I now have a rough form of f. So then I'm going to take the partial of that rough form with respect to y, and I get minus x plus h prime of y. And then we're going to set this equal to n. okay, which is 2y minus x. So that means that h prime of y, notice the negative x's on both sides, it's going to be equal to 2y. Right? To get to h of y, I'm going to go ahead and take the integral. All right, so up by 1 divided by a new one, I get y squared, and then this is where we get that c if you need it. So I'm going to go ahead and write my solution. That's up here with that a new h of y. There we go. Not bad at all. All right.